Hello everyone, my name is Alejandro Mera. I am a PhD student at Northeastern University. In this talk, I will present DICE, automatic emulation of DMA input channels for dynamic firmware analysis. This work was developed in collaboration with Open and my advisors Long Lu and Engin Kirk. I will start with an introduction and the context of the problem that we solve in this work. Microcontrollers, or MCUs for short, are small single-chip computers that execute firmware, which is a monolithic binary that contains all the software stack. MCUs are used in critical settings, including medical, automotive, consumer electronics, and IoT fields. That is the reason it is essential to protect these devices. However, security researchers are continuously finding new vulnerabilities in millions of already deployed devices. In many cases, vendors cannot patch these vulnerabilities, letting critical infrastructure at a high risk. Why securing embedded devices is challenging? The reason is that existing analysis tools have limited support for the highly diverse and heterogeneous MCU hardware. Essentially, firmware depends on diverse peripherals to interact with the physical environment and communicate with other devices. But the state-of-the-art firmware analyzers cannot fully model or emulate peripherals, failing to execute a large portion of the firmware code. Therefore, they miss opportunities to detect bugs. Let's take a look at this GPS example that motivates this work. In the green box, we observe the firmware interacts with peripherals using memory map I/O, but in the red box, we observe other peripherals use DMA to write or read directly from buffers located in RAM. As depicted in this figure, without supporting DMA, a large portion of the firmware is not executed. Like other peripherals, the DMA controller is diverse and usually not emulated, and that is the reason for many bugs surviving undiscovered in the firmware. To solve this problem, we present DICE. The goals of this solution are hardware independence to support a wide range of architectures, peripherals, and DMA controllers. Firmware compatibility to support all possible ways that firmware might use DMA. Dynamic DMA to track the creation and termination of DMA input channels dynamically. No source code to support directly binary-only firmware. Easy integration without requiring hardware or software not available in other analyzers. The design of DICE adopts a novel approach. Instead of emulating the DMA controller, we design DICE to identify DMA input channels when the firmware configures the DMA transfer into the DMA controller, and then DICE determines when the firmware reads from these input channels and signals the analyzer to provide input data for dynamic analysis. DICE uses a heuristic approach based on the life cycle of a DMA transfer. This life cycle starts with the configuration of the source and destination of a DMA transfer into the DMA controller, continues with the transfer, and finishes when the firmware accesses the DMA buffer. The firmware analyzer can observe steps 1 and 3, but the second one is exclusive to the DMA controller that we are not emulating. To identify the configuration, DICE filters the firmware write operations on step 1, looking for two pointer-like values pointing to specific areas of the MCU memory map. For example, in this figure of the Cortex-M memory map, the source is pointing to the standard peripheral memory area, and the destination is pointing to the beginning of a buffer in RAM. To identify the size of the DMA transfer, we use the step 3 of the life cycle. Using step 3, we design a conservative approach that expands the DMA buffer size as the firmware reads from the destination buffer. The buffer size is continuously incremented by observing read operations on the buffer's edge. And finally, when DICE observes a new configuration of source and destination in the DMA controller, it invalidates the previous configuration and releases the buffer. After this step, DICE starts a new life cycle for the next DMA transfer. This method supports the dynamic nature of DMA, which is not supported by other solutions that rely only on statically allocated buffers. We implemented two prototypes of DICE, the first on top of the state-of-the-art P2IM analyzer for the Cortex-M3 and M4 architectures, and the second one on top of a MIPS emulator for the M4K and M-class architectures. In both cases, DICE is a drop-in component that extends KeyEmu, which is the processor emulator of these systems. Regardless of the embedded architecture, MIPS or Cortex-M, the implementation includes three main sections. The first one implements the heuristic filtering to identify the source and destination of the DMA transfer. The second one manages the life cycle of the DMA transfer. And the third one creates hooks on RAM that can provide data from different inputs. In the case of P2IM, we use the AFL passing engine that later we use for pass testing. We evaluated DICE using unit tests for two purposes. First, to verify accuracy in identifying DMA input channels, and second, to measure DICE runtime overhead. We also perform fast testing campaigns to confirm that DICE support fast testing on real-world firmware, and found bugs that existing firmware analyzers cannot identify. The unit test is diverse in terms of software and hardware. For the software, it includes 83 benchmarks and sample firmware that use peripherals in different ways. For the hardware, the unit test collectively includes 11 MCUs, 9 different DMA controllers, 5 different vendors, and 2 embedded architectures. DICE is highly accurate. It identifies 89% of the DMA input channels, and in 95% of the cases, the DMA buffer size was inferred correctly. In all the test cases, DICE presents no false positives. We observe that the missed DMA channels are either by limitations of the heuristic or because the firmware analyzer did not execute the DMA-related code. The overhead of DICE is reasonably low. On average, it adds 3.9% to the execution time of the P2IM firmware analyzer, and in the worst case, the overhead is 11%. We performed fast testing for the Cortex-M architecture. We selected 7 real-world firmware from industrial and commercial IoT devices. It includes a Modbus library, GPS, CNC motor control, MIDI synthesizer, oscilloscope, guitar pedal, and a soldering station. These firmware represent diverse use cases of DMA, including streams for data signal processing and communication protocols with high throughput. All these firmware contain the complete software stack, including OS system libraries, drivers, interrupt service routine, and application logic. DICE discovered up to 79 times more paths in the passing campaign than the standard P2IM firmware analyzer. Also, in the case of the MIDI synthesizer, P2IM alone could not launch the passing campaign, because the firmware uses a DMA channel as the unique input. Therefore, DMA is mandatory for passing this firmware. Thanks to the DMA support, DICE discovered 5 unknown bugs with security consequences which P2IM cannot identify alone. We designed DICE to be generic. To work with other architectures, DICE needs 3 requirements. The first one, it needs that the architecture designates specific areas for RAM, flash, and peripherals. Second, the firmware uses the peripheral area to store the DMA configuration using MMIO operations. And the third one is that the DMA transfer follows the DMA lifecycle that we described in this presentation. Beyond MCUs, that is not applicable directly to devices that store DMA configuration in RAM. For example, some high-end MCUs or the Cortex-A devices. However, DICE can operate in cases where there is no standardized interfaces or operating system abstractions. Finally, DICE can be easily integrated with other analyzers. It needs access to the execution traces as the main requirement, which is quite common for analyzers based on QEMU, for example. Conclusions, we highlighted the importance of supporting DMA-enabled peripherals for dynamic firmware analysis. We designed and built DICE a drop-in solution that enables hardware-independent emulation for DMA input channels. DICE runtime overhead is low, and its emulation accuracy is very high. When used for passing real-world firmware, DICE increases code path coverage and helps to detect unique previously unreported bugs. Thanks for your attention. This is the end of my presentation. The source code of DICE, the benchmarks, sample firmware, and real firmware are available at the following GitHub repository.